So this is a fairly technical video on proving that how we get the equation of the least squares line from summary statistics. So first, some things to get us started. What are we going to do here? When we're dealing with a scatter plot, we have some x's and y's. For all of our theoretical work, when we're doing proofs, we're going to standardize things. We're going to change things to z-scores. So that means for each coordinate, we're going to take the value minus the mean divided by the standard deviation. Remember, this is the z-score formula. This is how we compute standardized scores. So for each ordered pair, we're going to do this. We're going to do like the x-coordinate minus the mean of the x's divided by the standard deviation of the x's. Do the same for the y's. And we'll get a new scatter plot, which looks the same, but now it's z-scores. And two consequences of it being z-scores that are going to be important are down here. First is that the mean of z-scores is always 0. So the mean of the zx's is 0, the mean of the zy's is 0. Remember, the way we get the mean is by adding up all of these zx's and dividing by n. So this implies, if I look at this equation here, n is just a constant. I can multiply both sides by n. And this implies that if I add up the zx's, if I add up the z-scores for all the x's, I always get 0. And likewise, the same is true for the y's. I get 0. If you're confused about the summation notation, I have a supplemental video on how the summation notation works, and you can check that out if you want. It's just a few minutes long. So the variance of the zx's, remember the variance is the standard deviation squared. The variance of the zx's has to be 1, because when I change things to z-scores, I'm dividing by the standard deviation of the original data set. That means the standard deviation of this new data set has to be 1. This was the definition of variance. Again, it's not critical that you be able to do this by hand, but this is going to be theoretically important in what's going to follow. Now, if I look at this definition of variance here, this is zx minus the mean of the zx's squared, and then I average those. Sum of them up, divide by n. But from up above, the sum of the mean of the z-scores is 0. So that means this right here is 0. So that implies that if I sum up the zx's squared, that turns into 0, so I can drop that out. And divide by n, I get 1. Or, another way to put this, if I sum up the z-scores squared, so I square each of them and then add them up. This is like this. I'm not squaring after I add them up. If I add them up before I square, I get 0. But if I square them all and then add them up, I'm going to get the sample size n. And likewise, if I square all the z-scores of the y's and add them up, I'll also get n. These are not things that it's critical that you know for the future of the class, but they're going to be theoretically important in the proof that's going to follow. So, before we go into the proof, I need to remind you how we define the least squares line. And this occasionally comes up in tests. The least squares line minimizes the sum of the squares of the residuals. So let me remind you what this looks like. I'm going to be dealing with z-scores for almost this entire proof. So, if I have an actual pair z-coordinate, zx, zy, and then I have some line, this may or may not be the best fit line. I have a predicted zy based on this line, and we're going to write the equations of our lines as mx plus b. And so this difference between the actual zy and the predicted zy
the difference between an actual zy and a predicted zy is what's known as a residual. And so this is zy minus zy hat. And since we're going to be using a line here to do our predictions, this is going to be m zx plus b subtracted here. So this is one of the residuals. The least squares line squares each of these things down here, adds them up, and the least squared line makes that sum as small as possible.
So our goal here is to minimize we want to minimize this complicated looking expression. We want to this is the sum of the squares, and these are residuals here. And remember, summation notation, this is going to go across every pair of zx and zy across the data set. This takes some careful work. We'll do it in 3 steps. So step 1, we will show that the least squares line always passes through the point with the coordinates mean x, mean y. So here's how I'll prove this. What we'll do is we're going to always be working with z-scores. Remember, with z-scores, the means are 0, 0. So here's going to be the logic of the proof. I'm going to have 2 lines with the same slope. One of them is going to go through mzx plus b, where b is non-zero, and the other one's going to go through mzx plus 0. So this one's going to go through the origin. This line is going to pass through the mean of the x's and the mean of the y's, which is 0, 0, since we're dealing with z-scores. And I'm going to show that no matter what m is, I'm just leaving m as a variable here, that the sum of the squares of the residuals using the line with 0 here is smaller than the sum of the squares of the residuals if I have a b here, which shows that no matter what the slope is, having the line going through the origin gives me a smaller sum of the squares of the residuals. Remember, that's what we're trying to minimize here. So let's look at what this looks like. So I'm going to compute side by side what a residual looks like here and what a residual looks like if I were to use this line. So here, the residual is I'm going to have my actual zy minus my predicted zy, which is going to be mzx plus b. So that's a residual. If I'm using this line, I don't have the plus b. So I simply have that. So the sum of the squares of the residuals then looks like this over here, and it looks like this over here. And what I want to show is that this sum with the sum of the squares of the residuals with the plus b is always bigger than this one. And you look at this and you may be like, well, this looks obvious because, well, this has got the b in here, this one doesn't. But remember, some of these values may be negative, some of the b might be negative or positive. It's not obvious just at immediate glance that just because I have this plus b in here, it's going to be a smaller sum than this one. It takes a little bit of work. So let's see what happens if I square this out. This one is a little bit easier if I square out. This is a bit of a mess. If I square this one out, I'm going to have the sum here in front. I'm leaving room here because this one's going to get bigger. And if I square this binomial, I get zy squared minus 2m zx zy plus m squared zx squared. That's what I get by square this binomial. I'll come back to this because I'm going to compare it to this one. We want to show this. Here I'm going to take 2 steps. So first I'm going to treat this as a single term. So if I square this, I'm going to get zy squared minus 2 zy. Then I'm going to have mzx plus b. And then I'm going to have this squared. Now, and I'm going to distribute this.
So I'll get zy squared minus 2. I'll just distribute this 2zy across here. minus 2m zx zy plus, or minus rather, 2b zy plus, and now I have to square this out. So this turns into 3 terms. I'll get m squared zx squared plus 2b m zx plus b squared. And then I'm adding a bunch of things like this up. Alright, that's a lot of symbols. But remember, what my goal here is I want to show that this has to be bigger than this. And we can't just say, well, look, it's a mess. There's so much more stuff going on here. So clearly this is greater than that one. That doesn't prove anything, because there may be negative numbers in here. There may be positive numbers in here. There's no guarantee that there's more terms that this is greater than this. We actually have to do some work. So let's compare. Let's compare this expression to this one. There's certain terms that match, and I'm going to cross them off. This has got zy squared, so does this. So those are going to be exactly the same. I don't need to worry about those. This has minus 2mzx so does this. So those are going to be exactly the same. Don't have to worry about those. This has plus m squared zx squared, so does this. So I can cross those off. So everything over here has been gone. So this over here is now a 0. Subtracted all this stuff away. And what's left over here is sum minus 2b zy plus 2b m zx plus b squared. And now I have to show that this is greater than 0. And this is going to go back to that previous page we were looking at, the first page with some of the shortcuts. Using my summation notation, this is a constant, this is a constant, this is a constant. So I can distribute these things in and factor the constants out. So what I get is I get this equals minus 2b sum zy plus 2b m sum zx plus sum b squared. This negative here, b might be negative, m might be negative, b might be negative, this might be negative numbers, but that doesn't matter, because if I go back to my very first sheet here, the sum of the z-scores is 0 for x and both for y. And here I have some of the zx's, some of the zy's, and so this is a 0, this is a 0, and so I get sum b squared. This is definitely positive because I'm squaring a real number. So in fact this is greater than 0. This shows that this sum is always greater than this, which shows that having the line go through the means, which for z-scores is 0, 0, always gives a smaller sum of squares of the residuals than any other line. That proves that the least squares line always goes through where the means are. This was the worst of them. Step 2 isn't so bad. Works out quite nicely. When dealing with z-scores, the slope of the least squares line is the correlation coefficient r. So what we've shown in the previous bit is that the least squares line always has to go through where the means are, and for z-scores that's the origin. So now I know my best fit line, my least squares line, has equations zy predicted equals m times zx plus 0, because the y-intercept is going to be 0. Now I need to determine what this value m is, and I'm going to show you that it's always the correlation coefficient. We're going to proceed as before. I'm going to write down what a residual looks like. So residual is an actual zy minus a predicted zy, and that's a zy minus mzx. Oops, from up here, and then I need to square these and add them up.
And I want to make this as small as possible. So I'm going to do a little bit of algebra here. If I square this, I get zy squared minus 2m zx zy. This is a z sub x here. It's confusing. Plus m squared zx squared. And then using the properties of my summations, this is sum zy squared minus 2m sum zx zy plus m squared sum zx squared. Now I have to go back to that first sheet again and notice, because we're dealing with z-scores again, the property of the variances is if I square all the z-scores and add them up, I get n. I get the sample size. If I sum all the y squared and add them up, I get n. So I have that here, and I also have it here. So this is n, and this is also n. N is the number of data points we have, the number of ordered pairs in this case. So what I get is I get this sum of squares of residuals turns out to be n minus 2m zx zy plus m squared times n. Now everything here, this is based on the data set, this is based on the data set, this is based on the data set. The only thing that can change here is the slope, m. I want to know what slope of this line here minimizes the sum of the squares of residuals, and I'm going to prove that it's the correlation coefficient r. So I want to consider this expression as a function of m. So think of this where m is the variable, it's the thing that's changing. And if I think of it as m is the variable, if I use some precalc notation, I say, okay, here's some function of m. This is a quadratic. I've got m squared, I have m, and I have a constant here. So let me write it like it might look in precalculus or in calculus. This would be n times m squared minus 2 sum zx zy times m plus n. So this is what it might look like as a polynomial as a function of m. I have something times m squared minus 2, this ugly sum times m plus n. But the reason I'm reminding you of the precalculus is this is a quadratic. We know what graphs of quadratics look like. They're parabolas, and since this first term is positive, this is an upward opening parabola. So if I were to plot this, this is just some number, this is just some number, that's some number. If I was to plot this as a function of m, I would get an upward opening parabola. And I want to, remember my goal here is to minimize this sum. But we know
for a parabola, the minimum value is going to be down here at its vertex. And if you remember your precalculus, if I have a parabola y equals ax squared plus bx plus c, this vertex right here, the vertex has x coordinate minus b over 2a.
So well, what are b and a in this context? Well, a is my coefficient of m squared, and b is my coefficient of m. So this is minimized when m equals minus b, there's my b, over 2 times a, for 2n, so that's my a. And the minuses divide away, the 2's divide away, and I get exactly the definition of the correlation coefficient. And so the slope that minimizes the sum of the squares of the residuals when I'm dealing with z-scores, the slope is always the correlation coefficient. Last step. This is the easiest one. What if I don't have z-scores? What if I have raw data? I want to explain. Now the least squares line has slope r times sy over sx. So this is a lot easier than the previous two. If you're feeling like you're overwhelmed, this is a lot easier. So let's say, here's how I'll explain it. Let's say you're doing some experiment in physics or something, and you've measured the motion of a vehicle, and maybe you've done it in the centimeters per minute. And so the slope of this line has units, centimeters per minute. And then you look over the instructions to the lab or whatever, and you realize that you've used the wrong units on these axes. The instructor has asked you to use millimeters per second instead of centimeters per minute. What will that do to your slope? Slope is your speed of your vehicle. What will that do to your slope? Well, remember, slope is y over x. It's going to have the y units over the x units. So to change centimeters to millimeters, you have to multiply by 10. 1 centimeter is going to turn into 10 millimeters. And to change minutes into seconds, you have to multiply by 60. 1 minute turns into 60 seconds. So what happens to your slope is you get the times 10, changing centimeters to millimeters, in the top of the fraction, but you get the times 60, changing minutes to seconds, in the bottom of the fraction. So your slope changes, gets multiplied, however your y coordinate changes, your unit changes. That's what happens to the top of your slope, but you get the change on the x coordinate on the bottom of your slope. What does that have to do with what we're doing? Remember, the way we get z-scores, going back to the very beginning of this, one of the steps in getting z-scores, when I go from original data to raw data, one of the steps, we also have to subtract the mean, but that's not a concern here. One of the steps is you divide by the standard deviations. So that's sort of a change in scale. It's a rescaling of my axes. I'm going x to zx, I divide by the standard deviation, and going y to zy, I divide by the standard deviation. Now over here, we've proved that the least squares line has slope equal to r. That was the previous page. Now I want to know, what is the slope of the least squares line going here? Well, I'm just going to use this idea. In changing from these units back to here, and if I'm going back, I have to multiply by the standard deviation of the y's, and I have to multiply by the standard deviation of the x's in going back. And since slope is change in y over change in x, I get this multiplication multiplying my slope, and I get this dividing my slope. And that's why
is r times zy over zx.
So I'll have another video where I do an example of putting this to work.